Yeah, let's start. Today we'll go over the module 13, Principles of Chemistry 2 or General Chemistry 2. We'll go over some very important and essential chemical equilibria backgrounds. We'll start with the chemical equilibrium. We'll define what chemical equilibrium is all about. As you can see, some chemical reactions do not react to their completion. So as soon as the reactants reacts to produce the product themselves will be decomposed to produce back the reactants. So when the reactants are reacting and producing the products, this is called the forward reaction, and the rate of this reaction called the forward rate of the reaction. When the products are decomposed and reverse back to produce the reactants, this is called the reverse reaction, and the rate of this reaction called the reverse rate of reaction. Whenever we have those rates are equal, then we speak about dynamic equilibrium. What is dynamic equilibrium? Dynamic equilibrium is a chemical equilibrium by which the rate of the forward reaction equal the rate of the reverse reaction, and that's what we mean by the dynamic equilibrium. And unique about dynamic equilibrium that both reactants and products are present at the end of the reaction. Correct? That's very important point we have to note. While in the real life, the chemical reaction which are not in equilibrium, you will see only products and the reactants are completely consumed. You will not see anything of the reactants left over. At the equilibrium state, concentration of the reactants and the products are not changed as long as there's no additional stress on the chemical equilibrium is practiced, such as we are changing temperature or volume or pressure or concentration or removing some of the reactants of the products. If that's not happened to the equilibrium will stay chemical equilibrium will stay at equilibrium, but as long as you are putting some external condition on the equilibrium, as we will see later on, the equilibrium has to offset this coming stress by moving to the side of the chemical equilibrium to release this or to offset this stress. And here this is shows you here. This is the rate versus the time. And you can see the forward rate of the reaction. That's for the reactants. They go all the way declining, correct? And the reverse rate of the reaction, that's the product side, they're increasing. That's forward rate of reaction decreasing by time, but decreasing. But it will come to the point that both rates, they don't show any change. They superimpose on each other, and the rate is said to be equal. And this range here, we have the dynamic chemical equilibrium. We can see this one here from the other side when we plot the concentration of the reactants and the products. The reactants are declining in their concentration, and the products is increasing in their during the reaction. So now if you look at this, the reactants decrease amounts decreases, but it will come to the point here. There's no change. If you look at this, there is no change in the concentration of the reactants, and in the same thing here, there is no change in the concentration or the amount of the products. So these two ranges here, the same thing. In this range here, we have our equilibrium. No change in the amount of the reactants, no change in the amount of the products, and by which the rates of the forward rate of reaction will equal the rate of the reverse chemical equilibrium. The chemical equilibrium is considered to be reversible and designated by the double arrow. If you look, you have a double arrow, you have chemical equilibrium. While on the other hand, if you have irreversible chemical reaction, not equilibrium, irreversible, always will be designated by one arrow. So one arrow means irreversible, double arrow means reversible. That's what you have, chemical equilibrium. Physical changes of the matter can be considered as chemical equilibrium. Physical changes just coming from solid to liquid to gas, or just coming from solid to the direct gas without going, without going liquid phase. So all these type of physical changes are considered to be part of the chemical equilibrium, although it's not really per se there is a chemical equilibrium, there's a physical equilibrium. Why? Because when we say chemical equilibrium, we are saying that a product is produced. In the physical changes, you don't produce any products, but the phase changes from one phase to the other, from solid to liquid to gas, but the compound or the reactant is still in the composition is still the same as the product, just the state of it changing. One of those is the iodine. Iodine is well known here. Iodine solid. You warm it up a little bit to turn to liquid. You warm it more, you can get vapor out of it. And the most important, this is the phase diagram. This is the solid range of the iodine. This is the liquid range, and this is the vapor range. Correct? So now we are interested in this point called the triple point. This point we can see this reaction is here. In this is triple point. You can see all three phases are present. Iodine solid in equilibrium with it, iodine liquid in equilibrium with iodine gas. This is a picture of the iodine. This is the solid here, and you can see the liquid is somewhere here. So just you can't see it very well. This is a hot plate, and this is the gas vapor. So you have solid, you have liquid here, and here you have the gas. Just an example of the physical change can be considered as equilibrium. Not chemical per se, chemical equilibrium. It's just, we can say it is a physical equilibrium because we don't change the composition of the reactants chemically. Here's another example well known, that's H2O. We have ice. Heat the ice a little bit, you get liquid H2O, and if you heat the liquid H2O further, you get what? You get the gas. And we are interested in this point here, which is the triple point, where you can find this here together, the three phases. If the solid, the liquid, the gas in this triple, called the triple point. Now we'll go to evaluate chemical constant. So how we can really evaluate the chemical equilibrium quantitatively. So we can only really assess and evaluate the chemical equilibrium by using the chemical equilibrium constant. And in this case, we use reaction quotient. So this is Q is the reaction quotient. So we have here ammonia is produced from the combination of nitrogen with hydrogen, produce ammonia. So the reaction quotient is always the reactants, the products, over the reactants. So this is the product here, ammonia, and the reactants. And we have to watch for the number of moles. Here is 2, here is 3. Here in front of nitrogen is nothing there, but it's understood, not written, is 1. So then you have the concentration of ammonia, power 2 squared, divided by the product of nitrogen concentration over 1 understood, not written, to multiply by the concentration, cubic concentration of hydrogen. So this is the 3 here. In front, the 3 moles will come as a cubic power there at the top. So this is called the reaction quotient. Now, and this is designated by C. C is the molar concentration for the reactants and the products. But sometimes, if we use the partial pressure of the gases, all those are gases, by the way, gases, and gases here. So if we use the instead of the concentration, the molar concentration of these gases, we can use the partial pressure instead. And then the QB, the reaction quotient, will be designated with the subscript P as a partial pressure. And it's the same thing, it's just the products over the reactant, the partial pressures of the products over the partial pressure of the reactants, and we have to watch for the number of moles will come up as powers. So here ammonia is squared, and nitrogen is O power 1, understood, not written, and the cubic power of the partial pressure of hydrogen. So let's see another example, and we have to watch now for a very important rule. If we have a liquid or we have a solid, we have not to consider them as part of the reaction quotient or part of the chemical equilibrium. The question is why? Well, it turns out to be the solids, and here is the liquid. Their concentration is large and it does not change. And therefore, we can consider their concentration constant, and we can discard them out of the formula or the expression of the reaction quotient and the equilibrium constant. So we don't need to consider them because there are no changes in their concentration. So they are not part of the chemical the chemical reaction quotient or the chemical equilibrium constant. So we are only, this is solid here, is out. We are only considering gas and aqueous. So gas and gas here and aqueous. Gas and aqueous here. That's the only one. Gas and aqueous. So if we have solid or liquid, we discard them. So let's look at the QC, the reaction quotient for the reaction A. So only is left the solid, only left CO2, and that's a product. So therefore, QC will be concentration of the CO2, correct. Let's look at the second question, the second equilibrium. We have gas, that's good, we can consider it. H2O liquid, no, that's not the case. Can they get rid of it? Aqueous, that's good, we can consider it. So there will be the product, which is hydronium ion multiplied by the chloride ion over the HCl gas. Those aqueous over G gas. So this is for B. C, we have to look. We have ammonium hydroxide solid. This is out. It's not considered. And liquid out again. It's not considered. What is the QC, the reaction quotient? Is it the product? Ammonium hydroxide ion, ammonium cation, ammonium ion, and hydroxide ion. So this is the QC. How about the last one? The last one here we have liquid. We don't consider it. This is out. We don't consider the liquid. And we have carbon dioxide gas and the aqueous of carbonic acid. So it will be carbonic acid, the product, over the carbon dioxide reactant. This one is here. So let's look further here. Now we'll go and look at some numbers for the QC and KC. So in this, we'll go through examples of QC and KC, or KP and QP, with using numbers. So we have this reaction here. Carbon dioxide reacts with H2O to produce carbonic acid. We said this is liquid. This is out of consideration, not part of the QC and KC. If 0.55 moles of carbon dioxide is added in, this is the volume, and this is number of moles. If you divided moles by volume, give you the molarity, correct? At temperature. At equilibrium, it is found the CO2 concentration is this. This is at equilibrium. And the carbonic acid, here it is, has equilibrium amount of this. So calculate the value of the reaction quotient before any reaction happened, correct? And what is the value of the equilibrium constant of the reaction? So we have to do the here is QC, and here is, we have to look at KC. So let's look at those here, and you can see at the beginning of the reaction there is no product, correct? We have really to note this. So at the beginning of, before any reaction happened, this is very important. Before any reaction happened, there is no product. So the product of carbonic acid is 0 molarity. There's no products produced. So the concentration of CO2, we can calculate it because we know the volume of the flask. We know how many mole we have added. So divide the mole, the number of moles by the liters here, you get this amount. Then the QC will be the product 0 divided by the reactant's concentration, you get this. So the answer is 0 because anytime you divide 0 over any number, the answer is 0. So QC before the reaction is 0. Now how about the equilibrium? And this is very important to look at. KC has to equal QC at equilibrium. If we have a system at equilibrium, then KC, the chemical equilibrium constant, will equal the chemical reaction quotient. They are equal. So now we plug all the numbers of the equilibrium values of the molarities are given, correct? You just plug in, this is the products over the reactants, and this is the answer here. Okay, this is 5 10 to minus 1. Let's look at the second example. We have HCl gas. Again, this is H2O, not part of the consideration. We have hydronium ion and the chloride ion. So now we have the number of moles, the initial concentration is of the HCl, of the reactant, 0.150 moles. And the flask is used is 1.00 liters. So if you divide the moles per liter, you get the initial concentration of the reactant HCl, correct? And furthermore, and then you can look at the equilibrium is given to you, all their concentration. The concentration of HCl at equilibrium is 0.075, and the hydronium and the chloride, they have the same concentration of 0.065. Let's go further. The question is, what is the value of the reaction quotient before any reaction? Of course, before any reaction, we don't have any product left. So before the reaction, the concentration of the product of the hydronium and the chloride is 0, correct? And the HCl, the reactant, is the moles given divided by the volume. It will give us this 0.150 molar of the initial concentration of the reactant HCl. The QC has to be 0 because the no products, correct? 0 multiplied by 0 divided by 0.150. So before the equilibrium, there is QC, the reaction quotient is 0. At the equilibrium, they are equal to each other. Then we put the equilibrium concentration for hydronium ion, the chloride ion, divided by HCl. Those are given to us, and here is we have the value. Now we'll look at this, and this is a very important. You might have to put this one here in a flashcard, so just to remember it every time, which is really is all about the prediction of the direction of the chemical equilibrium. So we have 3 states. Kc can be bigger as Qc, Kc can less than Qc, Kc equal Qc. So the Kc is the chemical equilibrium constant. In case it's greater than the chemical reaction quotient, then we say the reaction is really favoring what? The product. The reaction is in direction of the product, and therefore in order to reestablish the equilibrium, because the equilibrium just went beyond the equilibrium. So then we have some part of the products they have to decompose and produce back the reactants. So Kc favors greater than Qc, favors the product side. The reaction go to the right, but it is beyond the equilibrium, so it has to be shifting back to the side where there's less stress. Qc less than Qc, the system is below equilibrium. The ratio of the concentration is small, which we can say this is favoring the reactants. This is the reactants, favoring the reactants, and this is favoring the product. So this is the product, this is the reactants. Now, how about if they are equal? Then there is no favoritism. The both are equal, and therefore the chemical equilibrium does not favor any part, whether it's the product side or the reactant side, and it means the initial concentration equal to the will be equal to the equilibrium concentration. So this is very important. Keep it in mind, and we'll look at some example here. We'll see how the whole thing is moving which way. So this one here towards the product, this one here the reactants. Here is no moving. It does not. They are really in the what? In the equilibrium. There's no favoritism between both reactants and product. Let's do this one here. The reaction A plus 2B. Again, you have to watch for the powers here, and you have to watch for AQ. That's aqueous. Considered. All those aqueous and gases are considered. If you have liquid or solid, then we have to take it out. So the Kc is given to us. It says at particular moment at the time, the molarity of A is 0.4, the molarity of B is 0.5, the molarity of C is 1.1 molar, and D is 1.4. Predict the relationship between Kc and Qc, and the direction of the chemical equilibrium. Well, you just plug in Qc, all the numbers you have, correct? And this is at particular time. It's not given any time. So let's put all those together and watch out for the number of moles to be then come up as a power. The products will come over the reactants here, correct? And you plug in all those numbers together, and you get Qc is to be 17. However, Kc is, let's see here, Kc is 14. So it looks like Kc is less than Qc, correct? So it means it goes what? It favors what? The reactant side. It favors the reactant side. Let's look at this reaction. We have tetraphosphorus hexasulfide will react with sulfur. It give us tetraphosphorus decasulfide or decasulfide. So now if you look at this chemical equilibrium, all the information needed is given to us: the temperature, the Kc value, which is very important, and even it is exothermic reaction. It's giving off heat of 254 kilojoule. And we have 1 mole of each substance. So each reactant or product is 1 mole. And the volume is 1 liter. So you divide one mole divided by 1 liter, you get the concentration of each of those is 1 molar, 1 mole per liter. So now I plug in all those here, all numbers for the products and the reactants. You have just to watch for the sulfur here. The 2 will come up because will come up as here as a power. That's the reactant. That's the product here. Those are the reactants. So you get a value of 1.0. You look at the value of Kc is very big. Look, 6.2 10 power 3, and here is only Kc is 1. So Kc is bigger, so it favors the product side, correct? It favors the product side. So this is favors the product side, direction the product side. So now we'll go and look at the relationship between Kp and Kc. We said Kc is using the C is the molar concentration, and the Kb or the P is the partial pressure of the gases. So if we have the relationship between those two will be connected through ideal gas equation. This is ideal gas equation, which is here, correct? If I divide both sides by the volume, I get number of moles divided by the volume. Number of moles is really the molarity here. So this is the molarity, number of moles. So N over the volume is equal the moles, correct? So moles over liter over the, and this is the molarity. So then we can come up with the partial pressure is the molarity, and we can get the molarity out. So the molarity is the partial pressure over the gas constant multiplied by temperature in Kelvin. So at least do here. Here is showing you the relationship, how to drive Kb to Kc. Now you don't have to go through this, but at least you know how we drive them. The main thing is for us is this, especially this, Kb equal Kc RT delta N. What is delta N? Delta N is the product's number of moles, the sum of the product's number of moles, minus the reactants, the sum of the reactants number of moles, correct? And R is the gas constant, and the T is in temperature in Kelvin, and Kc is the chemical equilibrium constant, correct? Using the, of course, the molar concentration. So this is very important to memorize, but you don't have to worry about this. This is just to show you how to do it. What's the relationship between it? So Kb is Kc multiplied by RT delta N. Delta N, that's number of moles, the difference between products and reactants. Let's look at an example. When we look at the example, then we understand the whole thing. So let's tell me here about the delta N here. So delta N here will be, for example, for this example, I have the products, correct? And the oxygen is 1 minus 1 for oxygen, minus 1 for nitrogen, correct? Am I correct? Yes. So you can see this is delta N is, here in this case, is 0. Anytime, that's a 0, correct? Just to know how to get delta N, an example. Now, if I give you the value of Kc here, you can tell from the value of Kc where is the reaction will go. And this is very important to know. If the Kc is less, much less than 1, it means the reaction favors the reactant. Again, this is another flashcard point of view, correct? And in the second example, if the Kc or Kb is greater than 1, it favors the product. If the Kc and Kb equal 1, which is very rare, but it can happen, Kc and Kb equal 1, then there is no favoritism. It's not favorable. But greater than 1 here, it favors the products, correct? And less than 1, it favors the reactants, correct? So you can see here is very, very large number, so it favors the product. And here, for example, this is very, very large, greater than 1, so it favors the product. Let's go further and look at this. Kc is very, very small, 10 minus 10. So it favors what? The reactants. How about this one here? Kp is 34. This is greater than 1, so it favors what? The product. But here we have to calculate Kc. In this example, we have to calculate what? Kc. So calculate Kc at this temperature in Kelvin. For the reaction, this is silver dioxide with the chlorine gas. Will give you silver dioxide chloride, and the Kb is given to you. So Kc. So here we need to get the delta N. And the delta N is 1 for the product is 1 here. 1 minus 1 for the reactants, and minus 1. So 1 minus 1 minus 1 is minus 1. So that's just how to calculate the delta N. And the Kb is, from the formula, you have to put this one here in flashcard so you can memorize it. Kb is Kc RT delta N, correct? The Kb is given to you, 34.5. Kc is, you have to work it out. The gas constant is 0.08206 liter atmosphere per mole Kelvin, and the temperature is 303 Kelvin. So, and delta N is minus 1. So just do your math, cross multiply, and your Kc is 858. 858. So consider the following equilibrium. We have hydrogen plus sulfur, will give us dihydrogen sulfide, and we have given the Kc at 700 centigrade Celsius, and we have to calculate now the opposite is Kb. We have Kc. Kc is given to us, correct? RT, R is the gas constant, 0.08, correct? 206, and T is given to us to be in centigrade. If you look, let me look it up, is 700 centigrade Celsius. We have to convert it into Kelvin, which will turn out to be 973 Kelvin. You do your math here, you multiply the gas constant by the temperature in Kelvin, and then the delta N is your minus 1, multiplied by the Kc value, you get the Kb. The Kb is 1.35 10 power 5. Now, does the chemical equilibrium mixture contains mostly reactants or the products? Well, look at the values, very large than 1. So it has to be favoring what? It favors the products, correct? It favors the product. So let's look at the C of the same question. Now, if the equilibrium is rewritten as follows. Now, what we have in this reaction, if you look at this, we have, if you look at the reaction here, so we divide both sides by half, correct? So if you, let me go back and look, this is the reaction here, correct? So what I did, divided not by half, divided both sides by 2. We divide the whole thing by 2. So this 2, and this is 1 here, and this is 2. So if I divide both sides by 2, I get this type of reaction. Then it says calculate the Kb at 700 degrees. Well, the Kb is whatever you found here, correct? Kb is your value here. But now the delta N is not the same. Kb is the same value, but the delta N is not the same. Delta N is here 1 minus half, correct? 1 minus half minus 1. So it's minus 1. So you put the whole value and then over minus 1 you get this value, which is when you divide by 2, then you see the value is reduced itself and is favoring, when you divide the whole thing by 2, favoring the Kb is less than 1, favoring the reactant side. Now let's look at this an example, another example here, and it has A, B, C, the same thing. This is now, we have the Kb at 480, correct? And we have chlorine gas with H2O give us hydrochloric acid plus oxygen gas. Question is, what is the value of Kb for this reaction? Okay, now look at this. Watch out very carefully here. Very carefully. What we did here, okay, what we did here, we reverse. So we did reverse. So we reverse. Reverse. We did reverse the here the products is being reactant, the reactant being what? Product. So we reverse the whole thing. When we reverse the whole thing, I have a Kb. What will be my new Kb for this reverse reaction? It turns out to be Kb is 1 over Kb prime, 1 over whatever is given to us. This is given. So 1 over this will be 13.3. Correct? Just reversing. The same reaction, we reverse. Now, what is the value of Kb for the reaction? This is the same reaction now. Look at this. But we divided by 2. We divided by 2. We took the 2 here out. We took the 2 out. We took 4 now. Divided by 2 is 2 here. Correct? And here will be half. So it turns out you put your Kb, the same value you got. Correct? This is your value here from the original reaction. But now the delta N is not the same. Delta N here will be half plus 2, that's 2.5, minus here is 1 and 1 minus 2, it turns out to be half. It turns out to be half. So put the whole value. Kb is 0.274. Kb is 0.274. In C, it said calculate Kc in part B. Well, we have Kb, this is Kb here. Kc will be the gas constant, which is 0.08206. Temperature is 480 centigrade Celsius. You convert it into Kelvin, correct? And you set it up to be equal. That's your Kb. That's you calculate in B. So now this is your Kelvin temperature. This is your gas constant, and delta N is as we said, this is half. 2.5 minus 2 is positive half, and this is 0.274 from this value here. So this value here is here, correct? Do your math, and then you can cross multiply. You can get your Kc value, which is turned to be 0.349. The last topic is we go to over coupled chemical equilibrium. It is very unique in nature. You will see a lot independent chemical equilibrium are happening at the same time without dependence on each other, and that's and they are really very important for the ecosystem of our life on this on Earth. So those coupled, just to give you an example here, the coupled chemical equilibrium is very important. One of this example here is what's happened here in the ocean. Because we have a lot of CO2, carbon dioxide emission, that will lead to carbonic acid being produced in large amount. And this carbonic acid will be used to really to dissolve a lot of calcium carbonate in the ocean, leading in a lot of acidification of the ocean. When the oceans are so more acidic, they kill really the coral, and the coral reefs will be really killed, and millions of coral will be vanished because of this high acidity. The coral are made of the calcium carbonate, very well known. So when you kill those corals in millions, then there's a lot of food shortage for many marines lives around the coral or living inside the coral, and that's a very 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 strong issue of the climate change, because we consider CO2 is just global warming, but we don't see the effect of CO2 in really dissolving the coral calcium carbonate, which is the coral carbonate is needed for the coral life and growth. So the coral lives on this calcium carbonate, and when you dissolve it, you kill those corals. The coral are really refuge for many millions of marine life. So it's not only the global warming of CO2, we have another problem to deal with, which is another type of acidification of the oceans. And like an acid rain into the ocean itself, make it more acidic and killing a lot of marine lives. Another example here, we can combine what's happening at the coral reefs and the atmospheric pressure, so that they are two coupled reaction happening at the same time, and they are really not dependent on each other. So they are not really dependent on each other. So at the coral reefs inside the ocean, we have calcium carbonate dissociate to give you calcium, the solubility dissolve to give you calcium cation, calcium ion, and carbonate ion. The KSB, SB means solubility product, SB means the solubility product, similar to the what? To Kc. Similar to Kc. Products over the reactants. But we have to watch, this is solid, correct? So we don't consider the solid. Just will be the products over the solid. Solid is not considered. The KSB is just the product of the calcium ion multiplied by the carbonate ion. Now, at atmospheric environment, when you have a lot of emission inside of CO2 into the atmospheric air, so you'll get CO2 gas. We have a lot of water as in the clouds as vapor. So the CO2 will be dissolved with CO2, will be CO2 aqueous. The CO2 aqueous will come and react with the H2O. Now the H2O is from the clouds, so we have a lot of humidity and a lot of water inside the atmospheric air. So then you get produced is carbonic acid, which is aqueous. This carbonic acid, correct, end up in the ocean. What end up in the ocean? Dissociate to give you the protonium ion, the proton ion, and the hydrogen carbonate ion or bicarbonate ion. The bicarbonate ion is being dissociated to give you the proton or hydronium ion and the carbonate ion. So the carbonate ion is a very important item for the coral growing and living. So it's very essential component in the coral growth. So, and we can see this. We have the carbonic acid aqueous. It has Ka1 of this. The bicarbonate dissociate to give you Ka2 is this. Correct. So now we can look. One can conclude that the carbonate ion are coupled in the dissolution of equilibrium of calcium carbonate, as well in the increase of acidification of ocean. So we have this carbonate ion is coupled, you see, in the here we have carbonate as a product, and here we have as a carbonate, correct, for both. And that's what coupled really a dissolution of equilibrium calcium carbonate, as well as this is the dissolution, as well as increasing acidity of the ocean. And we can look at this here. We can combine all those together here, and we can look combining the both the dissolution, this is the dissolution one, correct, with the case B solubility product or solubility constant, with the formation of bicarbonate. So we have reversed this one here. If you look up, let's look up here, this reaction here, this reaction, if you look at back again so we have reversed this reaction. So this reaction is reversed. So we reverse this reaction to look how we can couple those two reactions together, and we can use this value as well. So instead of bicarbonate, we'll go back to carbonate, so we can couple it with the case B, so they can vanish. So here is carbonate ion is produced. Now when we flip the other equation, he is produced. Here is produced. So they cancel when coupled. When we add those two reactions, the carbonate ion is dissolved. So what we end up, we have calcium carbonate solid plus this one here, plus protonium or protonium ion or proton ion, give us calcium. It is calcium ion and hydrogen carbonate or bicarbonate ion. Now what is the K value here? K value will be, because we have reversed this reaction here, this reaction is now reversed, correct, 1 over. So this reaction, so we can get rid of the carbonate, because carbonate is the common factor in both the coral, the carbonate in the coral reefs dissolution and increasing acidity in the atmospheric air. So with this here, the overall K for this combined coupled chemical equilibrium will be KSB multiplied by the K here, the reverse of the reverse reaction, and this and it comes very large, 185. The answer is 185. When we come back in the second part, we will go through the Le Chatelet principle.